Hi, is it working? Cool. All right. Welcome to the ZK Apps Advanced Workshop. This is a part of the first ever SnarkyJS week, and afterwards we'll have a gather town. Afterwards we'll have office hours where you can talk to some of the developers, and we'll have a gather town on Thursday where you can meet some of the other ZK app developers in the Munich community and some of the previous builders from the ZK App Builder program that O1 put on. So today's workshop is about recursion, and there aren't really any prerequisites. The content of this workshop is definitely targeted at those who attended the intro workshop or who have experience with SnarkyJS, but it should be pretty fun and interesting for almost anybody. And it'll be recorded, so you can go back and rewatch it anytime. And the intro workshop is also recorded. So if you missed any of that, you can reference it and then maybe watch this after to fill in some of the blanks. So the idea is just generally focus on the big picture and have fun. The idea is, to kind of like let it wash over you and yeah, get the general idea. Don't focus too much on the specifics. So we'll be going over what is recursion. Then we'll talk about the game that we're going to implement, Mastermind, and we'll build a naive implementation. And then Gregor will walk you through adding recursion to the ZK app. And then we'll talk about where you can learn more, the ZK App Builders program, and have a questions and answers at the end. So the first question is, what is recursion? And probably lots of people know this, but a recursive function is just a function that calls itself. So you can see here we have a factorial function, and it checks if the number is greater than 1. It checks if the number is 0, and if so, it returns 1. And then it calls itself and decrements the number. And so it will do this over and over again until it hits a point where this if statement is no longer true. And so by writing the program this way, you can calculate factorial. And there's actually a lot of programming languages that are built like just on this paradigm. So Lisp is one of them, and Haskell. I don't know Haskell, but Lisp is definitely worth learning. It's super cool. And so we can see the power of recursion lies in the possibility of defining an infinite set of objects by a finite statement. And so this is a quote from a mathematician. But that's kind of the idea here is, our company is called O1 Labs, and that's kind of the idea, is that we can take not quite an infinite amount of stuff in our case, but a very, very large amount of stuff and compress it into something of a fixed size. And so, what's a recursive zero-knowledge proof? Well, it's a zero-knowledge proof of a zero-knowledge proof. Or more precisely, it's a zero-knowledge proof that can produce proofs that prove statements about prior proofs. And so this is how Mina stays 22 kilobytes. It validates all of the previous state by verifying. So the previous state is stored in a zero-knowledge proof, and then or I guess the previous transactions. And so it validates all of these transactions by validating the proof of these transactions. And then it validates proofs of the additional transactions and then bundles all of that into a proof. And it does this over and over again. And so that way we can keep the part of the blockchain that's required in order to get, current final state a fixed size. And this is actually also where we're going to end up doing with our game later on, is we're going to build something kind of like a roll-up for just the game, but it'll work in roughly the same way. And so it's maybe even like a more specific type of a recursive zero-knowledge proof, which would just be called an incremental proof. So we're using this property of recursion to do some computation, prove it, and then do more computation that's contingent on that first computation, and then prove that as well. And then we can do this over and over again. And so this is possible because Kimchi is a recursive. It's a snark that it supports recursion, and it's pretty unique in this way. There's not really any other proof systems that you can easily work with that support recursion and are sort of relevant in the context of blockchains. So we think, there's a lot of really cool things that people can probably build with this, and we're excited to see what directions people take it in. And so, what can we do with recursive zero-knowledge proofs? What kind of cool stuff can you build? Well, you can build so much cool stuff. So one of them is succinct blockchains. That's what Mina is. And then you can also build off-chain execution of smart contracts, which is what you would use SnarkyJS for. And then you can build horizontally scalable rollups. And so these are a little bit different than the rollups on Ethereum because you can validate a bunch of proofs in just a single proof. And so you can take, like 10 proofs that are the same size, and you can turn them into one proof that's the same size as each of the 10 individual proofs. And you can do this. We'll be doing this today in the context of a specific application. So that's really, really powerful. You can build, private and verifiable elections or private and scalable dexes. And then there's some other really interesting, like kind of more technical things you can build, like auditable machine learning, which is not a meme. There's actually like a lot of strong use cases for this, like synthetic assets and stuff. The performance is good enough that it's feasible for models that aren't I don't know, GPT-3. And then we have verifiable delay functions as well. So today we're going to build a native implementation of the board game Mastermind, and we're going to play it using a local Mina blockchain where every move requires a single transaction. So that sums in total to a lot of transactions in order to play the game. And then we're going to extend it using a recursive zero-knowledge proof so that we can play the entire game off-chain and then settle it just by submitting a single transaction to Mina. And so that's significantly less transaction fees. It's a significantly better user experience. There's a lot of reasons that you might want to do this. Okay, so we'll talk about what Mastermind is. Mastermind is a game. It's a 2-player limited information code breaking game. It was originally called Bulls and Cows, and it has kind of a history of being implemented on early computing systems. So it was implemented on the Cambridge Titan in the 60s, which is one of the earliest computer games for like a computer that kind of came before people started seriously specifying stuff. They just kind of built them. Later, it was implemented at MIT for Multics, which is a predecessor of Unix, which is pretty cool. And so it's well suited to our example for a couple of reasons that we'll get into in a minute, but then also just because there's a cool history of people, using this as a demo for building, early computers, and then, early operating systems, and now early, zero knowledge proofs. So the rules of Mastermind, this is kind of what the board looks like. And how it works is that a code generator picks 4 code pegs from 6 possible colors. And so they hide them in this little like door that you can see at the bottom here so that the guesser can't see them. And they're arranged in a specific order, and the code generator is not allowed to change the order throughout the course of the game. And so then the guesser submits a guess by placing 4 code pegs in the visible portion of the board up at the top here. And the first guess is usually basically random. They have no information to go off of really. There is a little bit of strategy in it if you kind of try to drill down a bit more. But the code generator responds by placing these red and white pegs next to each guess. And so these are hint pegs, and they kind of give some indication as to what degree the guess was accurate. And so for every peg that's in the right color and in the right position, a red hint peg is placed. So you can see in this second line from the top, we have a red peg 3 from the left, and we have a red peg 3 from the left in the secret code. And so we get 1 red peg. And so that means, you have the right peg in the right place, and it's the right color. And then for every peg that's the right color but is in the wrong position, a white peg is placed. And so you can see in this case, at the very top row, we have a blue peg, or 2 blue pegs to the right. But we have a blue peg 2 from the left over here. So the blue pegs, none of them are in the right position, but they are the right color. So we get a white peg. And then it's important to remember that red pegs always take precedence over white pegs. So what that means in practice is just that a single code peg will generate at most 1 hint peg. So for example, if you have a peg in the right position that's the right color, you get just a red peg. You don't get a red peg and a white peg. And so over time, the guesser uses the information on the board to generate a new and hopefully more accurate guess over time. So as you move forward, you can see kind of here on the example board, every time you have a sort of a view of all of the previous guesses that you've made, and you can kind of start to extrapolate some information as to what the code is by using this known information, until eventually. And so, the cycle continues on where the guesser guesses a new code, and then the code generator provides a hint as to how accurate their guess was. And so this carries on until either the code guesser has got 4 red pegs, which means they've guessed the correct code, or until they exhaust a predetermined number of turns. So on this board, I don't know, I think you have 12 or 14 maybe. I can't count it by sight, but we chose Mastermind for our example here because it kind of meets a couple of properties that make it really well suited to run through kind of quickly and without having to, the point of this is to demonstrate recursion. And maybe a little bit of a more complicated ZK app than you saw in the beginner's workshop yesterday. But the goal is to kind of avoid getting too much into the implementation specifics of the game and focus more on kind of what's going on in the bigger picture. And so this game is great because the code generator has to play in a deterministic manner. So the code generator actually has no ability to really kind of like strategize or choose what they're doing after they've picked their code. After they've picked their code, they have to respond in a totally deterministic way to every single code that the code guesser generates. And so that makes it pretty easy to implement, and it's also very straightforward to experiment with. And then the code guesser, this is also a really big deal. The code guesser can't have access to the code. So for example, you couldn't play this game like on a piece of paper with yourself. And if you made like I don't know, an application that did this, you would have access to the code. And so it would be basically pointless because you could just look at it. And of course, you could build like a more complicated program that made it kind of a lot of work to go look at it. But in theory, people could still find a way to look at it. So this is kind of our naive implementation of the game, which is a version of the game that you play by interacting with the Mina blockchain and by generating a new transaction every time that every time that the code guesser makes a guess, they generate a transaction, and then every time that the code generator provides a hint, they're also creating a transaction. So in the course of like, I don't know, the board earlier had 14 pegs, you could have 28 moves and have to pay 28 transaction fees. And so I'll kind of go through the structure first. And so we have this class called Mastermind, which extends smart contract. Most of this was probably covered yesterday in the intro workshop. And then we have a method called init, which is sort of like the constructor in a Solidity contract. This will be used to set the initial state of the contract before people can interact with it. And then we have only two methods, publish guess and publish hint. And guess takes in a guess, which is a configuration of pegs, and publish hint takes in a solution, which is the configuration of pegs that are stored under that little door. And so we'll have to store some state on the blockchain. And we'll just run through this really quickly. The first thing that we have to store is the last guess. And so the guesser has to be able to commit to this on chain so that the hint generator can prove that they're generating a hint that's relevant to the guess that they made. Because if you just sent the guess to the hint generator, they could do something like, if you guessed the right thing, they could claim that you guessed something other than what you did. And so then we have this solution hash, which is an important component of this also. And so this will store a hash of the solution. And this makes it so that the solution is committed to when you start playing the game, but also so that the code guesser doesn't know what the solution is, because it's obfuscated by being stored in the form of a hash. And so this is a sort of important security measure. And then we have these two chunks of state called red pegs and white pegs, and these are the hint pegs. So these will be updated every time that we do a cycle of turns. And then we have this thing called turn number, which will be used to keep track of whose turn it is, and then it's also used to check when the game is over. You can by just checking if the number is odd or even, we know whose turn it is, and then if it gets to a certain height, we know that we've used too many moves and the game is over. And so let's see, we have just 3 methods: init, and a solution, which is a configuration of pegs. And this is the solution that we're committing to for the rest of the game. So in this case, this is stored right in the smart contract. There are other ways you might want to do this if you were, building this game so that a lot of people can play it. But again, we've kind of went for clarity here. And so in the init method, we have to check that the solution that we were provided is valid so that the code generator can't create an illegal game that's unwinnable. And then we store a hash of the solution so the code generator can't change the code in the middle of the game. And then we set the last guess to zeros. So these are, in this case, we represent absent pegs as zeros. It'll become clear why absent pegs are important in just a minute. They help you keep track of when you're counting up red and white pegs, basically. Then we have the fourth step will be to set the red and white peg counts to 0, and then set the turn number to 0. And so, this is fairly straightforward. We're just checking that our solution is legal, committing to it, and then initializing everything else to 0. And so then we have this publish guess method, and this will take in a guess, which is also in this type of pegs, and we'll check that it's the guesser's turn first. So that's important so that you can't generate a bunch of guesses in a row, basically. And then we'll increment the turn number, and then we'll check that all the values in the guess are legal. And so again, this is important so that you can't sort of throw the hint generator, something that makes no sense. And then we'll update the on-chain guess state. And so that's a fairly simple method. And then we have publish hint, which is a bit more complicated. And this will take in the solution instance, which again is not stored on-chain directly in any way. We only store the commitment to it. So by using this solution instance, which again should stay the same for the course of the entire game. So the hint generator's behavior is totally deterministic, assuming that they play the game correctly. And we can actually guarantee that they play the game correctly using this method. And so we'll increment the turn number. And then we'll check that the provided solution matches the solution that the code generator provided when they started the game. So, we just make sure this number never changes. But we can't store it in the contract because then the guesser would have access to it. And then we count the red pegs and we count the white pegs, and we update the on-chain states for both of those. And so we'll jump to the code. And let's see. I think I have to switch my screen to this one. Whoop. Hopefully everybody can see this. I think so. And I'm also going to drink water really quick. So here's our mastermind contract. And so we just created all the scaffolding by running the ZK app CLI. Oops, sorry, what did I do? I think nothing on my end, but we'll have to go back to that in a minute. So, okay, so yeah, we get all the scaffolding code just by running the ZK app CLI. And then we get this mastermind contract. And so I'll zoom in just a little bit and get rid of the bar over here so that everybody can see it. And so, we're just importing a bunch of stuff from SnarkyJS. We're exporting pegs, which is this circuit value. So we're defining a specific circuit value for our configuration of pegs. And it's actually just an array of these field elements, which were addressed a little bit in the intro workshop yesterday. But if you want more information, there's lots of it in the docs website. And we have this constructor, which just takes in a number and turns it into a field, basically. And then we have this hash, which returns a Poseidon hash of the values of the pegs. And so Poseidon is just a specific hash function that we use because it's really efficient inside of snarks, more efficient than something like SHA-256 would be. And so, yeah, this hash function is used to create the commitment that we'll use. And it's worth noting also that we're not like salting this. Gregor will talk about this a little bit later on, but that's for the sake of just streamlining things. You would obviously want to salt this and come up with some way to keep people from being able to easily guess what the hash would be if you were doing this in real life. And so now we're going to define all of our state. And so we can see we have this thing called last guess, which is we talked about earlier. We have the solution hash. Should be pretty straightforward: red pegs, white pegs, and turn number. And so these are of some different types. We have the pegs type we just defined, and then we have fields here, and then we have this unsigned integer 32, which is a really cool type that we provide that I think makes zero-knowledge programming a lot easier than it is when you have to work just directly with fields all the time. So uint32 has cool features like you can do all sorts of stuff that's a headache when you use finite fields. And so under the hood, uint32 is still finite fields though. But we have this init method we talked about earlier, and so we're just going to check that the solution is valid so the code generator can't create an illegal game. And we do this just by iterating through all 4 of the values stored in this solution pegs type, and asserting that they're greater than 1 and that they're less than 6. And so this way, if they're 0, no, you won't be able to like set a series of pegs that are not real pegs, basically. And so then we're going to take the hash and store this on chain, and then we're just going to initialize last guess to 0000. So if last guess is 0000, we know that the contract is just initialized, because later on when we check publish guess, we'll make sure that you can't publish a bunch of zeros or any zeros actually. And then we'll set red pegs, white pegs, and turn number to 0. And so this method will be called right after the contract is deployed, before anybody interacts with it. The next 2 methods, publish guess and publish hint, will be called by users. And so publish guess takes in a guess, which is just a series of pegs again. And we get the turn number from the MENA network, and we check that it's the guesser's turn. Oh, this is commented out. Maybe Gregor will talk about why. But we can just take the turn number and mod 2, and then assert that this is equal to 0. And so if the turn number is 0, 2, 4, any of these numbers, then the guesser is allowed to take their turn. And if the turn number is 1, 3, 5, 7, then the guess generator won't be able to put a guess on the chain, because we're waiting for the code generator to respond with a hint. And then we'll increment the turn number. And so we just set the on-chain turn number to the turn number plus 1. And then we check that all the values are between 1 and 6. We do this the same way we did up there, just so that we're making sure that it's a legal guess. And then we set this guess to the on-chain state. And so that's pretty straightforward. And then we have this publish hint method, which is a little bit less straightforward, but we'll kind of run through it really quick. And so we do the same thing. We get a turn number, and we actually don't need to check that it's the code generator's turn here, because their behavior is totally determined by the last guess. So what that means is that if the code generator calls publish hint like 12 times, it'll either fail if they put something other than the correct solution in, or it'll just do the exact same thing in the event that they put the correct solution in. So they could call it 5 times or 1 time, and it's always going to have the same output until the guesser updates their guess. And so we increment our turn number again, and then we grab these 2 arrays of guesses and solutions from the on-chain state, or I'm sorry, I guess the solution comes from what we pass in. It's never stored on chain, and then we initialize these red pegs and white pegs so that we can count them. And we'll check that the solution instance matches the one that the code generator committed to when they deployed the contract. So we do this just by hashing the solution that's passed in here, and then asserting that it's equal to the solution on chain. And so this assert equals basically means the proof will fail. You won't be able to generate one if these things aren't the same. There's just no way to generate a valid proof unless solution hash and solution instance hash are exactly the same. And so there's actually no need to check that the values are between 1 and 6 here either, because they're checked when the solution is set. So you don't have to do all that work over again. So next thing we'll do is we'll count the red pegs, and we're just going to go, through all 4 pegs again, and we'll check if the guess at a given index matches the solution at a given index. And so this is a bool. And then we use this circuit if in order to make sure that the if statement here is constrained instead of using like a JavaScript if statement. That would not necessarily be a part of the proof. And so it would open the door for people who are really smart to be able to kind of like work under the hood and maybe find a way to generate false proofs. So that's why we have to use this instead of a normal if statement. And so you have this, this Boolean. Is it the correct peg? Well, if it is the correct peg, then let's take red pegs and add 1. And if it's not the correct peg, then we'll just return red pegs. So this will stay the same. And so that's pretty simple. We're just counting the red pegs. And then what we also do is we set the guess I and solution I to 0 if they match. And so this is that we can ignore them when we're calculating the white pegs. So you can think of this as if we find a white peg, then we're kind of removing both of the, if you find a red peg, then you remove kind of both of the code pegs that you use to generate this red peg from the board, so that way you can't count them again. And so it's pretty intuitive for humans to do this, but obviously, in the program, we have to kind of find a way to make sure that we're accomplishing this behavior. And a pretty easy way to do it is just to just remove the pegs basically by setting them to 0. And so then we'll count the white pegs. And so what we're doing is we have these two for loops, and so we're going to step through every solution peg for every guessed peg. So we go to one solution peg, and then we compare it to the 4 guessed pegs, and then we go to the next solution peg, and we compare it to the 4 guessed pegs, so on and so on. And so we check if the pegs are the same color, and we do this the same way we did up here, just check if they're equal. But now we're checking the guessed peg in the first index and the solution peg in the second index. If they exist, then they're the same color. But we have to make. So if this works, then they're the same color. But we also have to check that they actually exist. And so we do this just by making sure that the guess is greater than 0. Because if it's a red peg, then we set it to 0. And so we have these 2 booleans, which are: is it the correct color, and is it not a red peg? And then if this is the case, we just look at, is it the correct color, and is it not a red peg? Well, if it is, then it's a white peg. And so if it's a white peg, then we're going to add 1 to the white pegs. And if it's not a white peg, then we're just going to return white pegs, and the white pegs will stay the same. And so then what we'll do is we'll remove these code pegs that were used to generate these white pegs so that we don't count them again. And again, the only interesting thing here is that guess and solution are these are different indexes because we're counting them separately here, basically. And so yeah, we just set them to 0. Otherwise, we set them to what they were before. And then we simply update the on-chain red and white peg counts, and that's the end of the turn. And so the players will go back and forth calling publish guess and publish hint until eventually, again, we didn't implement anything to stop the game after a certain number of moves or give somebody some sort of money or token if they win. But you could certainly implement that. That's just all sort of for the sake of clarity here. And so I'll switch back to the presentation really quickly. Let me just figure that out real quick. Oop, there we go. And so yeah, now I'll pass it off to Gregor for adding recursion. And so this is the cool part.
Thanks, Jack.
You're welcome.
Oh, can you reload the slides? I think I added this pretty recently.
Yeah, I can. No worries. Does this look better, or?
I don't see it.
Oh no. Is this what we're looking for? Like this?
I still don't see slides. But...
Oh wait, I'm sorry. I'm not sharing my screen anymore, I think.
Yeah.
I wonder why I did that. Okay, so this looks good though.
Yo.
Okay, really weird. So the text goes away when you make it full screen. I don't know why, but we'll just do it this way.
Oh no. Okay. Okay. We'll manage. Cool. So what I will give you is a little feature preview. So recursion SnarkyJS is still in development, actually, but yeah, we just made it work this week, and yeah, soon it will be published, and you will also be able to use it maybe next week or the week after. So what can this do? Now it works. So recursion means that you can verify proofs inside other proofs. So you all know we have smart contracts, and now smart contracts have methods which you call when you create a proof, and now these can also verify other proofs. And you can also make any assertions about those proofs. So that's the first thing. Smart contract can merge in proofs. The second thing is that if we want to create rollup type architectures, we also want to create proofs that are not related to smart contracts. So just proofs for execution of anything, because smart contracts prove something a bit more specific. They prove that you create a certain transaction. So that's too specific for our general purpose rollups. And yeah, and rollup proofs are the same as smart contract proofs in that they can also be composed, merged into each other, and so on. And yeah, if you want to check out, if you want to run the same code that we do, then you can actually check out that branch. So, and soon it will also come to npm. Can you go to the next slide? Okay, so we're talking a bit about the new objects that you get. So we now have a type proof, which is, this is a simplification, but that's the most important things that you have to know about proofs. They can be verified, and they have a public input. So obviously, when we get a proof, we can't see what the private inputs were. That's the point, right? But it's important. It's really important that we can look at the public input and maybe make some assertions about it, compare it with something else, process it, because that gives the proof its meaning. If you would just get a proof and could only verify it, yeah, it wouldn't mean much. So that's why the public input is an important part of this. It's the part of the proof that is interesting to us. Okay, yeah, go further. Okay, so now how are proofs integrated into smart contracts? It's very simple. Proofs can just be passed as arguments into methods. That's it. So previously you could pass in. No, sorry, I want to go back. Can you? Yeah. Previously you could pass in circuit values as method arguments, like for instance fields or bool or uint32. And now you just also can pass in proofs. And inside the method, you would then call proof.verify. If you don't do that, it doesn't get verified. So that's maybe a bit of a gotcha. We may need some error message or anything like that. But it's actually a bit more flexible. You can also optionally verify based on some Boolean value. But this is the most important thing. You can verify them, and you see that the proof has a public input on it. And for instance, we could say, we assert that the public input is such and such. So a classical example is, say that proof proves that it's a CK Oracle proof, and it proves that you went to some web page where you read out your birth date and created a proof that you're over 18. Then maybe that public input would be your age. And then we could have proof.public input, and we could check that your age is, for instance, over 18. So that's how you use the public input. Okay, next slide. Second thing, how proof integrates with smart contract is that obviously you can return proofs from smart contracts. So this is the API to create a transaction that you probably know from the last workshop. And on such a transaction object, you have a method transaction.proof, and it will return the list of proofs of all the ZK app parties that were involved in that proof. And so you can have multiple accounts interacting in one transaction, and some of them will create proofs and some will not. And if one of them creates no proof, then the object in the list will be undefined, and yeah, otherwise it will be a proof. So the most typical case is just you create just one proof by calling just one method. Okay. So that was the smart contract side. But now, as I told you, we also need non-Mina related proofs. And for this, we created a new primitive, a new building block, which we tentatively called CK program. It's a bit like a CK app, but CK app is already a term that was taken, so we call it CK program. API names are subject to change. Hey, yeah. So we're actually interested in your feedback on this new API. This is also a bit of an experiment because, as you see, it's not a class this time. It's a function, because we wanted to try out how that feels. It has some advantages. So most of our, I can say most of the people in our team, I think, prefer an API like this. But of course, we have the existing things that are based on classes, and which also have some benefits. For instance, in a class, you get this, and you can do lots of, you can do magical stuff that you can't do here, for instance. Yeah, so I will walk you through this new API. So CK program is basically like a smart contract. It's the same. It's on the same level, So a CK program consists of a list of circuits. We call them methods, like in a smart contract, and all those methods have the same. What they share is that they have the same public input, and the public input is also what will be on the proof that you create, the statement of this program, if you want. And the methods field. So the public input is like it's like a circuit value that you already know, and the methods field is an object with arbitrary names, with arbitrary keys. So this my method, that's a user-defined name, and this is basically the name of your method. And because we're not using classes, we also don't have decorators, and in general, this API is a bit more explicit. So we have a field called private inputs, which actually lists the private inputs. So it's not magically read from the function signature, which was also a bit error prone, created lots of complications in my opinion. And just passing it in as an array of types, so of classes or other types, makes it so much easier, in my opinion. So we are explicitly declaring what the private inputs are, and in this case, it's just one thing. It's one proof, and then we declare the method, the actual circuit, if you want, and that works just like before in the smart contract. So, except one difference to smart contracts is that the first argument is always the public input. So you don't really have this in smart contracts, because in smart contracts, the public input is a bit implicit. It's basically the transaction you create, and you can modify this and access these transactions with this dot something. Here, because we're not in a class, we just explicitly pass in the public input as the first argument. It's always the first argument. And then for instance, you have a proof, and you can make a statement about the proof. Okay, let's go to the next slide. I don't see anything. Oh, it's to the code already. Great. Oh, can you go back? Sorry, I forgot one thing. At the bottom. Yeah, how you use this. I don't know if you really see it. No, you okay. Yeah, if I change my window size, I can see it. So at the bottom, it says it shows you how you can create a proof, and it's much simpler than with smart contracts. You just do my program dot my method, Yeah. So the API is await my program dot my method, and that creates a proof. It's a much simpler API, which is one of the benefits we get because we don't use classes. Okay, I'll share my screen now and show you the mastermind code. All right. So, is this a good size? Okay, I'll try to go with this. Okay, to the top.
Oh, that's good.
Cool. So this is basically the same thing that Jack showed you before. We just changed some things to make it. Yeah. So as Jack said, we try to do everything off chain and only at the beginning create a proof that is posted to the chain. So as before, we had pegs, but now we will not define a smart contract. Instead, we will create a CK program, and because we create a CK program, we need a public input. And the public input is it's very similar to what you had in smart contracts with state. So it's basically you can think of it like some sort of state or event that gets emitted by the proof. I don't know. Yeah. So this is very close to what we saw before, but instead of defining state with @state on smart contracts, we now create a circuit value for the state. And yeah, it's just the same thing. We have a last guess, we have the solution hash, red pegs, white pegs, and the turn number. And sorry. Yeah, so this is it. And this state becomes a public input. So that means if you get this proof, you can inspect what the state is. You can look at it and say, oh, this proof has the last guess such and such, and the red pegs are such and such. So the proof can basically make a statement about what the execution. Next, we go to the methods, and as before, we have 3 things here: init, publish. Oh, I have a typo here. That's ugly. Okay, publish guess and publish hint. And this, I will show you how this corresponds to the smart contract version. So we declare the private inputs. Those are the pegs. And now we have the method. So the private input is the solution here, because we initialize and what's initialization for a CK program. So it's not really the same as for smart contract. It just means this will be the first proof that you create. We will create a chain of proofs, and in it we'll create the first one, and then our other steps in the game will take earlier proofs, merge them in, and move the state a step further. Okay, so in this init method, we do exactly the same things. We check that the solution we got was valid. It has values between 1 and 6. And now it becomes different because we don't have state.set and state.get, but we have this public input we can operate on. And this public input is basically the output of that function call. So it's a bit confusing. It's a new state that this method will attest to. So it's a bit backwards that you have to pass in this new state. But that's really what that's what the result of a smart contract execution is also under the hood. In reality, the things that you use, like from the chain, those are really public inputs. So here it's the same. Or if you say in a smart contract, if you create an update, if you do state.set, that actually defines the public input. And yeah, so under the hood it's the same thing, but it's more low level because this is the low level primitive basically. So public input is our new state, and so we assert that it is such. It is what we want in the init method. So the init method requires that the public input, the new state, has a certain form. So we check that the solution hash equals solution.hash. We assert that the last guess is initialized to our zeros, and so on. So this is just asserting that this is the initial state that we want. Okay. And here I have written the lines that we had before in the smart contract, and you see that it's pretty easy to translate a smart contract into this new thing. It's basically, if you set something, you have to assert that the public input equals something. And in the next method, I'll fold this and fold the next one. Oh, okay. Now we have publish guess. Same thing as before, we got a public input. We have the guess, that's the private input. And here's the new thing. So the method now not only gets the public input and the guess, but also a previous proof. And you see that the previous proof has type self-proof. That's a little that's a trick so that we not have to define a custom class for this. But if it's self-proof, it will know that this is a proof for this CK program. The input could also be a proof from another CK program or from a smart contract, and then you will have to create a custom type class for it. But if it's self-proof, it's just this one. So that makes it easier. So we get recursion with this. And okay, first line, don't forget, we have to verify that previous proof. That means it will get verified inside the circuit. Okay, now how do we update our state? First, how do we get the previous state? Of course, to get the previous state, we look at the previous proof. The previous proof has a public input, and that public input is this mastermind state that I defined, and it has a turn number. So before we had grab turn number from the Mina chain, now we have grab turn number from the previous proof. That's the translation that we have to do. Okay, we check. Okay, we do everything as before. Check that it's our turn. And to increment the turn number, we increment it here. And we assert that the public input of this proof is the incremented turn number. So maybe get some used to think about it like this, but I think you will get used to this. Okay, and we also update the guess, and to update the guess, we check that the public input that we got is the guess that we put in. So publish hint. I don't think there's that much to say here. It's just the same patterns again. So for instance, if we publish a hint, we modify red and white packs. And to modify them, we look at the public input and check that these are really the new red and white packs that we computed here. Okay. Awesome. So let's look at how we can use this. we have a secret program. It's a bit like a smart contract, and we yeah, I will talk about that later. Let's look at the file that uses this. So we import this mastermind thing. Remember that this was this CK program we created. And first of all, we have to generate our verification key and our approval key. That's what we call compiling. So we do mastermind compile. And this takes about 20 seconds. And it's actually the slowest part of everything. Proving is a bit faster. Okay, we define a solution. Now we do this initialization, which means we create the first proof in our chain. And do you remember that so this is how we call our methods on the ZK program. We say .init, pass in this is the public input, the mastermind state, and the initial solution. But to do that, we have to create this public input first. So it's a bit, we actually have to basically write the same methods twice. One method which just creates this state, and the second method which asserts that it's the state that we want. So let's look at this mastermind helper.init. It was in the other file. So this just returns, it just returns the initial state. And we have similar things for publish guess. I gave this the same function signatures as the proving method. So this gets a guess and a previous proof, and to create a new state, it takes all of what was previously in the state and changes the parts that publish guess should change. Okay, so it's a bit ugly that we have to do this twice, but actually we will have a way to make this unnecessary, because there's already work on the OCaml side to enable pickle circuits to have a public output, and the public output is it's the same. It's also a public input in crypto terms, but you just have to return it. So you don't have to do this doing it twice. So you just return it, and then that's it. You don't have to you return it from method directly. I'll show you this another time when it's ready. Okay. So how does this flow works? I see I'm a bit late on time already. Is it okay? Do you think it's okay if I take like 10 minutes more?
Yeah, we can go over a little bit. And
okay.
Also, I didn't run my code because I noticed we were late on time, but maybe you can run the normal code first and then show the recursive code. You don't have to if you don't want to, but
oh yeah, I see. Yeah. Sure, that makes.
Yeah, just so that people know that it actually runs. Yeah.
Oh, did you show this, Jack? Did we have this? Oh, you didn't show this.
No. Yeah, you can. Yeah. I
so okay.
On the screen, but
people will.
The idea is just to run something so that people can see it run, because that's fun.
Okay. Let's run it.
But we can't see because you're locked on the VS Code window.
What?
Or maybe can other people see it?
Oh, okay. Maybe like this. Can you see it?
I'm not sure if I'm frozen or if
you're frozen.
No, I think. Let me see. I'll try.
Wait. What happened now?
Yeah, so if it's stuck, just refresh the page.
I mean, can you see my code?
Yeah, we're good now. Yeah, sorry, I think it did the same thing it did to Jason yesterday.
Okay, weird. Okay, let's move on. Let's not run it. Doesn't matter. Because I think it's important to talk about the flow that we will have here. So when you have a smart contract, the flow is on your user's device. You create a proof, you post it on chain gets updated in some way. Someone else does it again, posts another proof. So it all happens on local devices, but you immediately post your updates as transactions. So what are we doing here? We don't want to do that now. Okay, so we imagine that this is like a server that has a service which is you can play a mastermind game with it, and somewhere in the beginning of the lifetime of this server, it will create this initial state, maybe, or maybe when you have when you make some request, it will create this initial proof, and then you will fetch this initial proof. You have to fetch this initial proof from the service, and now you can make a proof. Okay, you will make a guess now, and the guess is a number of pegs, and you run this non-proving function to create this guess, this object, which is the same as the public input, and then you create your proof for guessing something, and then you have your own proof here, the user proof. Okay, and now you would now post this proof to the service, and it's his turn to now publish a hint. So his hint will also be proof, no? And you see that the proof I create here, the user proof, this gets posted to the server, and the server takes this and passes it in as the new previous proof to his publish hint method. So it's like it merges it in and it creates a new proof in this chain. So we'll also create a proof for publishing the hint, and so on. So we could now take this proof and see what this was about. We could see, okay, the server published a hint that said we have, I don't know, some red pegs and some number of white pegs. Okay, so you can read it off it, same as your methods can read it. Okay, next, now it's back to the user. Same thing, and now he actually creates the correct guess. So this is the final round. You will post it to the server again, and he will publish another hint. And in that hint, the pegs, the red pegs will be 4. So it will have all red pegs, and that means you won the game. Okay, so this final proof is a proof that you won the game. It's a proof that you have guessed the code correctly. Okay, so now what do we do with this final proof now? So all of that was off-chain. Oh, do you have a problem again? Resharing? Okay.
Gregor, try refreshing again. I don't know what's going on, but
yeah.
It works for me. It doesn't work for other people, which is like weird and intermittent. And
okay, sorry. How do I
Oh, it's okay. No.
How do I
Crowdcast being weird.
Why don't we use a well-established product for this?
I think, yeah, we gotta go on Twitch. We can have some fun Twitch streams.
Can you see it now?
SnarkyJS Twitch stream. Yeah, we can see it now, I think. What about, let me know in the chat if you can see it. Okay, perfect.
Yep, can see it now. Okay. Should I repeat anything or CK proof that refresh works? Eventually, hopefully I will. Okay. Cool. Yeah, I think you got the idea just from me talking about it. So we end up with this off-chain computation that produces a final proof where you can read off that this represents a successful game of Mastermind. And now we want to integrate it. And so what can we do with a proof like this? Of course, we can now post it onto the Mina chain and verify it in a smart contract. So that's what we are going to do now. In this case, we actually have to create a custom class that describes this kind of proof. So what we have to do is we have to give it a type. That's the public input type. This is for TypeScript, and this is for runtime, the runtime. We have to specify it twice because we can magically read the runtime object off of the type. Okay, so we have a public input type, both of which are mastermind state. And we have to give it a tag. So the tag, I don't know if this is a good name, but that connects it to the CK program. If you remember, mastermind is our CK program here. It could also be a smart contract. So you can basically always interchange smart contracts and CK program. So this tag could also be a smart contract. Okay, so this now sufficiently describes this final proof that we have. And now we write a smart contract. I called it mastermind rollup. It's very simple. It just has a state that says that someone won some game of mastermind. This could probably be more refined. For instance, you could publish which user provided this proof and publish the address of the user or something else. Okay, we will just have a state that someone won the game. And we only have one method, which is publish completed game. And to use that method, you have to have this final proof. You pass that final proof to the method. It's a mastermind proof, what we created here. We verify the proof. And now we have to make an assertion about it, namely proof public input, the red packs, have to be 4. That means the game is won. That's the only thing we do with the proof here. And now we can be sure just with these 2 lines that this proof describes a game that was won. And if this succeeded, then yeah, someone won the game. And we set that state. And that's it. So it's basically everything, and everything else I have is stuff that you already know. How do we deploy this rollup smart contract? And we make a transaction that publish this proof of a completed game. And as you notice, this is just one transaction. So we have our efficiency gains. Cool. I think I'm done. Maybe if you can go back to the slides one more time to wrap
yeah,
up.
absolutely. Yeah, let me see. We'll go. Oh, sorry. Every time it does a different thing. Let me get. Oh my gosh. Whoop.
I actually have one more slide where I just say.
Yes, sorry.
A couple of more words and then.
Okay, can you guys see it?
Yeah, I can. Can you go to the next slide? Okay, so we saw that application-specific rollup pattern. I hope that many of you will use it. You can roll up many things into one transaction. Next. This has a couple of benefits. Next slide. Yeah. So you have, it's easier to have concurrent interactions because you don't have to deal with the Mina consensus or anything. You just have this one sequencer which can easily order transactions as they come in and produce new proofs as you want to produce them. This can give you high latency, lower fees, and yeah, you can check out the code. It's Jack's repository here, mastermind. Yeah, not that important, but there are also a couple of nits that I had with the naive smart contract that Jack showed you. So there's also a more advanced version that addresses these shortcomings.
The nits are good, but some of them are quite in depth. And then I should also add, we'll have a tutorial that goes in depth on this as soon as the recursion API is final.
Cool. Okay, I'm done. Do you want to take it over?
Yeah, sure. I'll go ahead and take over. Thanks, Gregor. Okay, I think you're seeing my slides now. How do we make that big? There we go. Okay, awesome. Thank you, Jack and Gregor. That was awesome. Let's talk about where to learn more. If you were here yesterday, you saw the same slide. We had the docs, and also join us on Discord in the ZCAP developers channel. But then also I wanted to mention 2 more things, which is check out blog.on labs.org, because we will be starting a new series every month about what's new in SnarkyJS. So that's a great way to stay informed of just brief bullet point features of what has changed. And then in the near future, not sure exactly when, but soon, we will also start weekly office hours for ZK apps. So keep an eye out for an announcement around that. And then I wanted to talk about the Builders Program briefly. If you're joining for the advanced workshop, you're probably a great candidate to apply for the Builders Program. We ran a Builders Program last year that went really well and had good feedback on that. And we were able to get a lot of good feedback for improving SnarkyJS and ZK apps, and also help developers ramp up on learning both ZK apps and SnarkyJS. So we decided to run another cohort of the ZK Builders Program. That's going to be 3 times as large. But we'll actually have 3 sub-cohorts. So 3 groups of 10 developers each that will go through the program together. So you'll have the chance to learn at the same time as other ZK developers. It's a 3-month program, and you can work on any ZK app or ZK app related project of your choice. And you can come with some ideas and then brainstorm with the O1 Labs team to sort of finalize and land on an idea. And then also selected participants who finish the program will also receive a grant from the Mina Foundation. So that's a nice incentive to apply. So we will share the Builders Program link in the chats, and please come join us. So let's open up to Q&A, and Brandon, if you would like to come on the stage, feel free to.
We can just start, I think. Or I wonder when should we take this to the office hour? Because then we could have like everyone could speak. So
I think we can just take it to the office hour now, maybe, unless you guys can meet us there. We can also do it here, but I don't think Brandon is here.
Are there any questions that you saw that you'd like to answer on the cardcast while we're still here?
Lots of questions.
Yeah,
but,
actually, that's
I think we can. No, I think we can go to the other thing and still answer. Just do a section first where we just answer these questions. What do you think?
That sounds good to me.
Just keep it open.
The benefit of doing it here is we would have it on the recording too for other viewers.
Oh, gotcha. Okay, let's answer a couple of questions, I guess.
Okay.
Cool.
Okay, Brandon just slacked me. He's got big problems on his end.
Okay. I just start. Like the one I'm looking at is, wouldn't another TS annotation like verify that would verify that the param always like a higher order function to the trick? I think this was about the fact that you had to prove that verify. And so this is a deliberate choice on my end, basically, because there are also situations where you want to only optionally verify the proof. And we have actually another method called verify if. So this gives you additional flexibility. And I just wanted to expose that functionality because it's already built in Pickles, and I think it would be extremely hard to replicate if we wouldn't expose it. So yeah, and to do that, you have to explicitly do something, either verify or optionally verify. So that's the reason. Otherwise, we could just have done it automatically. Matej asked, what if you check arguments for type of proof and auto-verified? Yeah, that's the point. So we don't always want to auto-verify it. There are situations where we want to conditionally verify on some Boolean, on some bool. That's why we don't do that.
It could potentially save a lot of time if you have, like, I don't know, multiple proofs going in and you want to verify only a subset of them based on some sort of condition.
Not sure if it saves time. I think it's the same number of constraints if it's optional.
Oh, you're right. Okay, never mind.
But for instance, we had this init method that created the first proof, and then we had other methods that took in proofs. But it would be actually possible to write just one method that always takes a proof, and if it's the initial state, it doesn't verify it, and otherwise it verifies it. And the first time you just pass in a dummy proof, and then you get this initial thing. You see what I mean?
There's also a good question here. Somebody is asking about the example of verifying an age in a proof. So saying like someone's over 18, how do you keep that information private? So with zero knowledge proofs, because you're running that smart contract client side in the browser, you can have that private input being your date of birth, for instance. But then the smart contract can say yes or no and return a Boolean that basically just says, is that condition met? And so that's what the proof represents, is that a particular condition is met, but it doesn't actually contain the data itself.
Actually, it's probably worth Gregor diving a little bit more into this, because this is specific to a slide on the let me find this right slide. It's this one. So yeah, let me. I can't share my screen, but this is specific to this thing called public input in the ZK program part of the API, which also might change. So I don't know if you have more to say on that, Gregor.
I have one more thing to say, which I think is an important point. is that the public inputs, the proofs that get passed in are not public, and the public inputs on them are private inputs. Okay, so for instance, say we want to create CK oracles, then we could just create a proof that attaches to the entire HTML. But like all the HTML is the public input, and it says, I went to this page and got this HTML. Okay, so obviously you don't want to expose that to anyone, but if you pass it into a new method, that's a private input. Your HTML that you got is a private input if you pass that proof into a new method, and then you can process it and read out something like, okay, my age is this, and create a new proof that only says, okay, my age is such and such. And this new proof is, again, reusable. You can use it for one service that requires age more than 21 and another service that requires age more than 18. Because it has a public input, it's important to be able to pass data with the proofs.
There's another question here about data types and circuit value. So it might be worth mentioning just for the video. Circuit value is kind of like a struct, if you're used to that in other languages. It's like a compound data type that you can create that works inside the circuit. And these guys can add more too if you want.
Yeah, which perhaps we should rename, because circuit is an implementation detail that we probably shouldn't expose to people at this abstraction layer, in my opinion. But I guess if you have an opinion on that, check GitHub issues coming soon for a thread.
Yeah, we love naming suggestions for sure. Okay. Well, maybe we should go over to the office hours then.
Cool.
All right, great. Thanks for joining, everyone.